Okay, so here's our inclined plane without friction. We have a car on a ramp, and the ramp has an incline of theta degrees. What we're going to do is we're going to use a really great trick in physics. We're going to draw our axes rather than straight up and down. We're going to draw it along the direction of motion. So this will be my positive x. This will be my positive y. And this way we can set up our free body diagram. I'm actually going to go to the next slide here because this is really a pseudo free body diagram that they have listed. What you would do, for example, on an AP test is you would just label the normal force, and then straight down would be the force of gravity, which is the weight of the car, which is mg. Okay, so this you draw first, and then you would go and break up your vectors into components. So okay, so here we go again. Here is the angle of our ramp. What we know is that this angle is theta for the reasons that I went through in class, where if this is a right triangle right here and this is theta, then we know that this is 90 minus theta, and then this is a right triangle, so, or right angle, so if this is 90 minus theta, then this has to be theta. So that works out well for us. And what we're going to do is we're going to take this force vector and we're going to break it up into its components. So here we have the y component of the force of gravity and the x component of the force of gravity. Now the only thing you have to watch out for is that this is now our opposite side and this is now our adjacent side. So we know that force of gravity is mg, so the component of that in the y direction, FGY, is going to be mg cosine theta, and then our FG in the x is going to be mg sine theta. Okay, now at this point we don't pay attention to him. Now we just have all of our components that are acting on the car to get it to move down the ramp. So we can sum our forces in the y direction will be equal to the mass times the acceleration in the y direction, but we know that there isn't any, so we know that it will end up being 0. And we look at our free body diagram, so we have force normal minus mg cosine theta is equal to 0. So the normal force in this case is going to be equal to mg cosine theta. Okay. Over here in the x direction, we have the sum of all the forces in the x equal to m times the acceleration in the x direction. In this case, it does accelerate down the ramp. There's no friction, so really the only force in the x direction will be mg sine theta is equal to max. These masses cross out. You are left with the acceleration in the x direction is equal to g sine theta. And as you can see, there's no mass in that equation. So the acceleration for this car, it could be a car, it could be a penguin, it could be a truck, it could be a physics book. It doesn't matter what the mass is. It will always have this acceleration. It's only dependent upon the acceleration due to gravity and the incline of the ramp. So if you looked at the extreme cases, when theta equals 0 degrees, then the sine of 0 is 0, which makes this whole expression ax equal to 0, which should make sense because it would look like this. Here's the car on a horizontal surface, no incline whatsoever. There's not going to be any acceleration. You then take the next extreme, where if it looks like this and theta equals 90 degrees, well, the sine of 90 is 1, and 1 times g just means that the acceleration is going to be equal to g, or in other words, it would be in free fall. We can then take this and we could take it another step further, and let's do that on here. We found that a is equal to g sine theta. We could ask you questions such as, how long does it take to reach the bottom? We could ask for the final velocity if it starts from rest. As long as we were told, let's say the distance down the ramp equals d. Well, from here, you could set up your kinematic equations and you could say VI, VF, displacement, acceleration, and time. We know it started from rest. We could find that. We're calling that d. The acceleration is g sine theta. And we could find out the time that it takes to get down to the bottom of the ramp and how fast it's going. So pause the video for a moment and try it out. Okay, so check it out. We just picked out an equation that will lead us to time, and we end up with the square root of 2 times the distance it travels divided by the acceleration due to gravity sine theta, which is really the acceleration. And then the final velocity is 2g sine theta d square root. What you want to look at is that, again, mass does not matter. It's only dependent upon the angle and the acceleration due to gravity and how far it's accelerating. So the length of the ramp. All right, great. Check in on the next example, the next video.